Hi. Last lesson we looked at springs and we were looking at Hooke's law, how force and the extension of a spring are related. Today we're looking at springs again, but we're looking at the energy that's stored in a spring. There's a calculation that goes with this one as well. But let's start off with some simple questions. 5 equations for energy. Yesterday was 4. What's the difference between elastic behavior and plastic behavior? What is the equation to work out the spring constant? And on a force extension graph, which quantity goes on which axes? Pause, answer the questions, and then unpause when you're done. Okay? So the 5 equations for energy, there are loads you can do. Work done is force times distance. GPE is M times G times H. Kinetic energy is half mv squared. Energy is equal to power times time, and energy is equal to QV, charge times potential difference. What's the difference between elastic and plastic behavior? Elastic is basically remove force, return to normal. No, return to original. With plastic, so that's elastic. Plastic is basically remove force, doesn't return. Say right then, doesn't return to original. What is the equation to work out the spring constant? Well, the spring constant equation F equals Kx. So F over X equals K. On a force extension graph, which goes on which axis? The force is on the Y and the extension is on the X. Now, you would normally do that the other way round because what you choose is independent. And so therefore you would normally put that on the X-axis. But because you want it on the other way around, because you do the gradient, and that'll give you the spring constant. I was supposed to have animated that, but I didn't. That's quite silly. What's the work done equation? Oh, there it is. Work done is force times distance. Now, you have both forces and distances involved in the application of spring. Remember, force is equal to Kx. Force is equal to spring constant times extension. But if we do force times distance, it's not the same as the work done on a spring because there's more things happening. So normally, for example, I want to know the work done on pushing a box. I have to know the force that I'm pushing the box with and the distance I've moved the box. And the force I'm pushing the box with is related to how heavy the box is and friction and all the rest. But normally, when I'm pushing that box, the box isn't trying to pull its way back. But with a spring, when you're stretching a spring, the spring is actively trying to pull you back. And there are so many more things involved. So the energy in a spring, the work done on a spring, is more complicated than the simple work done equation that we'd normally use for moving something. In fact, the work done or the energy stored in the spring, there's more than one way to work it out. You do work when you stretch a spring because you exert a force over a distance. The force that you apply changes as the spring stretches or compresses, so you need to be able to apply this to an equation. The energy transferred in stretching is equal to 0.5 half multiplied by the spring constant times by the extension. Energy transferred also is known as work done. So E, the energy, is equal to half kx, which is also the same as half fx squared. So the energy in a spring is half times the spring constant times k. I realise I've just done that wrong. I moved my squared in the wrong place. It's half kx squared. Sorry, I knew something was wrong. Because f equals kx. And so if I put half fx, that's half f or kx x, which is the same as half kx squared. Apologise, I said that wrong at the start. Energy is half kx squared, spring constant squared, or half fx. If I said anything before that was wrong, I apologise. Let's do some questions, forgetting about my mistakes. Read the following statements and underline whether each is an example of elastic or inelastic behavior. A spring is stretched and returns to its original shape. Is that elastic or not elastic? A spring is stretched and remains stretched. Elastic or inelastic? A piece of wet chewing gum is stretched. Ugh. Is that elastic or inelastic? A rubber band is stretched and then released. Elastic or inelastic? Just write numbers 1 to 4. Elastic or inelastic? Oh, plastic. It's okay. Done that? Excellent. Another way to work out how much energy is stored in the spring is to look at the energy area under the graph. You look at the area under the graph, that will tell you how much is stored in the spring. Now, it's not always springs that you do with this. Sometimes you can do elastic bands. Sometimes you can just do materials. But the shape of the graph tells us a lot about that material, whether it's elastic, whether it's plastic, whether it obeys Hooke's law or doesn't obey Hooke's law, what happens to it. Bizarrely, if you look at this elastic band doesn't obey Hooke's law. Even though Hooke's law was all about springs, elastic band isn't as a springy as a spring, so it doesn't obey Hooke's law. How do we know it doesn't obey Hooke's law? Because it's not really a straight line. It's got loads of... There's no real straight line. And so basically this graph is, at the start, I don't have an elastic band dot. Here's a band on the end of my face mask. But at the start, with your elastic, it takes a while to get it going. And then once you've started stretching it, it stretches quite easily. And then at the end, it gets to a point where you can't stretch it any further. That's what's happening here. Here at the start, quite a lot of force, not much extension. So it's quite stiff at the start. Then, once you've got past the first bit, it loosens up. And then you need to put not as much force. So this is probably twice the amount of force as the first bit, but you probably have 3 times the extension. So stiff at the start, and then it loosens up a bit. And then when you get to the end, it goes back to being a bit stiffer. Doesn't extend much. So that graph tells us how that elastic band behaves. Now, copper is very different to an elastic band. Copper, here, up to about this point on the graph, copper obeys Hooke's law. The force and the extension were directly proportional. And in fact, up to this force, if you took the force away, that copper spring right back to its original shape. But here, after this point, you can see that all of a sudden, I'm hardly putting any force in, and it's getting a lot longer. That's because the copper stopped being elastic and started to behave in a plastic way. I know copper is a metal, its behavior is plastic. And so what would happen, for example, so you stretch it, it springs back, and then all of a sudden you stretch it too far and it just goes and draws out. And here at the end, that's where it breaks. This one is strange for glass. You're saying glass obeys Hooke's law. At the start, glass obeys Hooke's law. You may remember last lesson, I broke this piece of plastic. This would be similar. I pushed it a bit and let go, and it returns back. with glass, you can do a tiny bit of movement. But then I went too far and it snapped. And it just snapped in half. So it didn't do any of this bit like the copper did, where it goes like this. There's no plastic behavior, which is bizarre because this is plastic. Glass definitely doesn't have any plastic behavior. You can push glass a little bit, it might bend a little bit, but it'll go back to the way it was. Hooke's law. If you push it too fast, graph stops, smashes, broken. Someone's hurt themselves. So, looking at the graph of the force and extension, you can learn a lot about the material. If it's a straight line, equals Hooke's law. Straight line, Hooke's law. If it goes horizontal, generally means it's plastic or behaving plastic. If it goes up, if it has no plastic, then it snaps. There's a couple of extra definitions. So if we go back to the copper one, so this copper goes up about here. It's called the limit of proportionality, which means it's the point where it doesn't obey Hooke's law. It's a straight line from there to there, straight line, which is what Hooke's law was. The force and the extension were directly proportional. If it no longer directionally proportional, it is at the limit of proportionality, which means it no longer obeys Hooke's law. There's a little bit above that, about here, where it starts to curve more dramatically, and that's called the elastic limit. So this is, we'll call that P, and that's E. So this is where, P is where it stops being a straight line completely, and E is where it starts to curve a bit more dramatically. So somewhere around here. And that means it's no longer elastic. If I take the force away beyond the elastic limit, it won't go back. It won't go back to its original size. It is now gone into the plastic region. The elastic limit, anything below the elastic limit, the material behaves elastically. Anything beyond, it behaves plastically. The limit of proportionality, it stops being proportional, stops obeying Hooke's law. So it's no longer a straight line for the origin. And here we go. Oh, my head's in the way. Look at the graph below to the side, which shows the behavior of a spring that has been extended by adding different loads to it. First thing it says, question 5, determine the extension of the spring when the force applied is 4 newtons. You just have to read 4 newtons from one axis. What does it correspond to on the other axis? Easy. There's 4. Get a little ruler on your screen. Determine the force required to produce an extension of 18 millimeters. Find 18 on one axis, go across to the other axis. Calculate the spring constant from when it's behaving elastically. It's behaving elastically. Work out the spring constant. How to work out the spring constant? Calculate the energy stored by the spring when it's extended to point X. Good. There's multiple ways, remember, to do that. Area under the graph is a good example. Or use the energy equation. Don't forget to write down the numbers of the questions you're answering. Make it nice and clear. The graph below shows how the extension of copper changes as the force was applied to it. Copy the graph and label using the words. Oh, we talked about that just a few seconds ago. They spelled the word force wrong. But copy, these are the words. Somewhere the wire snaps, somewhere there's the elastic limit, and somewhere there is the limit of proportionality. Copy, add those labels. It's number 9, you can do that. Done. Here we have 3 different materials. My head's in the way for one of them. I reckon the top one's copper. I just recognize it. The graph below is the behavior of 3 materials. Use the graph to answer the following question. We'll say, this. Can I move my head without ruining the video? Mild steel. Okay, let me add that. Mild steel. Okay, Which material requires the greatest load to cause it to extend when behaving elastically? Which one do you have to put the biggest force on to get it to extend? Which material is the first to display inelastic behavior? Explain. Cast iron and concrete are often used to make industrial springs. Which of the two materials has the highest spring constant? How do you work out the spring constant from one of those graphs? Gradient. How does the energy stored by the cast iron compare with the energy stored by the concrete at their maximum extension? Can you work out your answer? That's it. Right. I believe in you. You can do this. Answer your questions. Make sure you label them nice and clearly so it's easy for your teacher to see what's happening. Okay. Love you. Bye.